Now we're going to talk about another way that we can describe a data set. We can describe a data set in terms of variability. And you might remember that variability has to do with differences in the data set. If there's no variability, then everything in the data set would be the same. And if there is variability, that means we have differences in the values in the data set. So just like measures of center, there are three main measures of variability that we'll actually be talking about in the course. So first of all, we have the standard deviation, which is the average distance of data values from the mean. So the standard deviation tells us something about how data is dispersed from the mean, how it's different from the mean. We then have something called the range. The range is the overall distance between the minimum data value and the maximum data value. And then we have something called the interquartile range. And this is essentially the range of the middle 50% of your data. So to find the interquartile range, which we sometimes actually refer to as the IQR, we find what's called the 25th percentile, or quartile 1, and the 75th percentile, or quartile 3, and then we subtract quartile 1 from quartile 3. So again, we're getting just the range of the middle 50% of the data. And we'll talk in a little bit about how we find those numbers, how we find the quartiles, and why we might want to focus on the interquartile range rather than something like the overall range or the standard deviation. Now I wanted to actually go through an example by hand, a small example, just so you could see how the standard deviation is computed, because I would like you to really have an understanding of what it is, or what the standard deviation represents. What does it tell us about a data set? Remember, it's the average distance of data values from the mean. So here's a very small data set again. We're starting with a small data set because you'll see that the calculations can be somewhat tedious. So if you had a very large data set, you'd obviously want to use technology. To start off with, you would first calculate the mean. So what is the mean of this data set? So again, to find the mean, we just take the numbers and we divide by our sample size. So that's going to give us 18 divided by 3, or 6. So that's the average, that's the mean of the data set. What do we want to do next? Next we want to calculate what's called the variance. The variance, again, is the average distance of the data values from the mean. So you might think, okay, I need to find the distance of the data values from the mean, and then I need to take the average of those distances. So maybe you're initially thinking, well, I'm going to find how far away the mean is from each value. Something like this. So I'm taking each of my values and I'm subtracting the mean. And then I would just divide by the total number of data values to get an average. So intuitively, it might make sense to try to approach it like this. Well, there are a couple problems with this. One problem is that you might notice if you figure out what the numerator is, you're going to actually end up getting 0. And that's because you're going to have some negative distances and some positive distances, and they're going to cancel each other out. So here you would have -5, here you would have 1, here you would have 4. If we add -5, 1, and 4 together, we get 0. So that would be a problem. And so because we don't want that to happen, we actually need to square these values in our numerator to avoid ending up with 0 and not being able to compute anything. So that's one thing we have to do. So I'm going to get rid of this here just so we're not confused by these additional numbers. Another thing that you have to do is you actually don't divide by the sample size, you divide by the sample size minus 1. And the reason we do that is a little bit complicated. It goes beyond the scope of our course, but essentially it just turns out that doing that is going to give us a better estimate of what's going on in the population. So it's been shown that dividing by n minus 1 rather than just n, or rather than just the sample size, gives us something that is a better estimate of the true population standard deviation. So we figure out the distances, we square those distances, add them all together, divide by sample size minus 1. And again, I encourage you to do this on your own to figure out what we might end up getting. And so what I got when I did this is, I believe I got 2.1, but let me double check my calculations before I write that here. So I'm going to pause a moment and come right back. Okay, so I think I said the wrong thing just there. Actually, when you figure all of this out, you end up getting 25 plus 1 plus 16 divided by 2. That's going to give us 42 divided by 2, or 21. So I think I might have said 2.1 in my last few breaths. And no, it's not 2.1, it's 21. So what do we do now? So we have this measure of the distance of data values from the mean, but we had to square all of those distances in order to avoid things all adding up to 0. So this number 21 is actually in squared units, and that's not very helpful to us because our original units of analysis were not squared. So what we end up doing now is we take the square root of the variance, and that's what the standard deviation is. The standard deviation is the square root of the variance. So S is the symbol we use for the sample standard deviation. That equals the square root of 21, or approximately 4.6. So we can say that the values in this data set are approximately 4.6 units away from the mean. That's what the standard deviation tells us. It tells us the distance of data values from the mean. Now again, we're never going to ask you to compute this by hand. So I worked through a very small example, but it was really just to show you where that number comes from. When you see a standard deviation, I want you to have an understanding of what that's telling you about a data set. And I wanted you to see this process of squaring things along the way to end up getting the variance, and then we take the square root of that to end up getting the standard deviation. Because of the fact that we do all of this squaring up here to get our variance, the standard deviation is never going to be negative. The smallest it can be is 0. So you'd have a standard deviation of 0 if there's no variability in the data set, if all the data values are the same. It's either going to be 0 or it'll be a positive number. It can never be a negative number. So that's an important thing to keep in mind. So another thing we want you to keep in mind is not only just what that number tells you about a data set, but we want you to be able to look at some histograms, such as these ones. And we want you to be able to think about which of these histograms would have a larger standard deviation and why. So again, visually, what does the standard deviation look like? What does it look like to have a large standard deviation versus a small standard deviation? So look really carefully at these two distributions. Which do you think would have a larger standard deviation and why? Or do you think they both have the same standard deviation? So think about approximately where you think the mean would be in these distributions, where you think the average would be. And look very carefully at how the data values disperse around the average. Is there one distribution where the data values are closer to the average than the other? So I would argue that in this second distribution, we have more deviation from the average. So in both of these, it turns out that the average is right around in here somewhere, between 2 and 3. So notice in this first distribution that if you look at the heights of the bars, the heights, remember, tell us how many individuals fall within those intervals. You'll notice that most of our data is right around the mean or close to the mean. And we have a few that fall out here in the tails, but not really that many. Compared to the second distribution where there's some data around the mean, but the majority of the data values fall further away from the mean. So the fact that those values are falling further away, that's increasing the distance of data values from the mean. And that's leading this second graph to have a larger standard deviation. So what do you think about these histograms? Which of these do you think might have a larger standard deviation? Or would the standard deviations be the same? So what are you thinking here? I'm hoping that with this first set, you're again thinking that this distribution would have a larger standard deviation compared to this second one. And why would that be? Well, again, look at the fact that the overall range of data values here is from about 1 to 12. Here it's from 0 to 8. So in the second distribution, we have a smaller overall range of data values, and that means the values are closer to the mean. A larger overall range, again, is increasing that distance of data values away from the mean. Now, the second two might be a little bit more tricky. So again, think about whether in one of the distributions we'd have more data falling closer to the mean than in the other distribution. Or is there one distribution where there's more data falling further away from the mean than in the other distribution? So some of you might be looking at the second distribution and saying, well, it's really bumpy here. To me, that means more variability. So I think that the second distribution will have a larger standard deviation. Unfortunately, that would be incorrect. So I can see why you would be reasoning like that and thinking that, but look at the overall range of values along the x-axis. So always pay attention to that overall range along the x-axis. If one data set has a larger overall range, then that's going to increase the standard deviation. So in this first data set, we have values that range from 0 to 6. In the second one, we have values that range from 1 to 5. So here we have more data values falling further away from the center, from the mean, than we do in the second distribution. In the first distribution, we have 3 data values that are between 0 and 1. We have 3 that are between 5 and 6, and then we have 3 in all of the other columns. And those values that are further away out in the tails, they're increasing that distance of data values from the mean. They're increasing that average distance of the data values from the mean. So this first one would have the larger standard deviation. And finally, I just wanted you to see what it would look like if we had the same standard deviation. So here in this first set of graphs, what you might notice is we have the same distribution, but we've just put it on different places along the x-axis. So the way that the data values disperse from the mean is the same, it's just that the values are different. The mean is going to be different in each case, but the standard deviation will be the same. And in the second graph, what hopefully you can see is that this second distribution is just a mirror image of the first. If we just flipped over the first distribution, we would get the second distribution. Again, the way that the data values deviate from the average is the same in each case, except they're just the mean would be different. So we're changing the averages, but we're not changing how the data values disperse around the average. And that, again, is what the standard deviation tells us. It doesn't matter what the average is. What's important is how the data values deviate from the average. So I'm going to wrap up here because in our next video we're going to start talking more about quartiles and how to find the interquartile range. And then that'll lead us into a discussion of what box plots are.